All right, today we're going to dive into a really mind-bending idea, one that messes with something we all just kind of take for granted about reality itself. We're looking at a brand new theory of gravity that asks a pretty wild question. What if the space we're living in isn't perfectly three-dimensional? Okay, let's get into it.
So it all kicks off with this huge, classic cosmic puzzle. You see, when we look out at galaxies, the stars way out on the edges are spinning ridiculously fast. So fast, in fact, that the gravity from everything we can see, all the stars, gas, and dust, shouldn't be nearly strong enough to keep them in orbit. Seriously, they should be flying off into deep space. So what's the cosmic glue holding them together?
For decades now, the front-runner explanation has been dark matter. The idea is that every galaxy is wrapped in this gigantic, invisible halo of some mysterious stuff, and all that extra mass provides the gravitational grip they need. And look, it's a solid theory, but it's not the only game in town.
So yeah, this galactic spin mystery, it's the anomaly. It's the crack in our cosmic understanding that really forces us to hunt for new physics, and it's where brilliant new ideas have a chance to shine.
But what if we've been asking the wrong question the whole time? A 2026 paper from a researcher named Achyut Rateria throws out this totally radical alternative. Instead of adding more stuff into space, what if we need to rethink the nature of space itself? What if the missing gravity isn't from missing matter, but is actually baked into the geometry of space-time? And that brings us right to the heart of this thing. The theory says that maybe the number of spatial dimensions isn't just a fixed, universal constant of 3. What if, instead, it's a dynamic field that can actually change from place to place?
The theory introduces this concept called the effective spatial dimension. You can see it's defined as 3 plus this tiny little deviation, a field they call epsilon. Now, epsilon isn't a whole new dimension you can walk through. It's more like a local measurement of how much space deviates from being perfectly three-dimensional.
You know, a great way to picture this is to think of space-time not as a perfectly smooth sheet of glass, but as having a subtle texture. In some spots, where epsilon is doing its thing, space might be infinitesimally stretched or maybe relaxed, and that changes how gravity behaves there.
Okay, hold on. This is the big, obvious question, right? If the dimension of space can wobble around, why does our entire experience just scream 3D? Why isn't reality some kind of chaotic mess? Well, it's a great question, and the theory has this surprisingly elegant answer.
Okay, this part is just super clever. Let's walk through the machinery that basically forces space to be 3D. First up, the theory defines this variable x, which is just a way to measure any deviation from 3D. Next, it borrows this powerful tool from a field called information geometry. Think of this function as creating a kind of energy landscape for the dimensionality of space. And here's the kicker, step 3. This function has only one lowest point, its absolute minimum energy state, and that happens only when x is exactly 1, which means exactly 3 dimensions. Any other value has a higher energy cost. It's like space is lazy. It always wants to settle into its most stable, lowest energy state, and that just happens to be 3D.
So space wants to be 3D, but we've established it can deviate a little, and when it does, it has consequences. That tiny little deviation doesn't just sit there. It actually generates what looks and feels just like an extra force of nature.
So here's how it works. The paper suggests that particles, stars, planets, us, we don't feel the raw space-time. We feel a version that's been slightly stretched or warped by this epsilon field. And if you're a particle moving through a space that's being stretched like that, the effect is totally indistinguishable from an extra force pulling on you, a fifth force.
Now, this is crucial. It's not random. The theory lays out a fundamental rule for how this epsilon field has to behave over vast distances. It predicts that the field should get weaker with distance, or R, according to a very specific power law. It has to be proportional to R to the power of -1/9.
And this is just beautiful, right? It's the cause and effect, spelled out. A field that falls off as r to the -1/9 creates a force that falls off as r to the -10/9. That exponent isn't just some random number they pulled out of a hat. It's a direct, sharp prediction. It's a unique fingerprint that we can actually go out and look for in the universe.
But there's a catch, right? A single universal force law can't possibly explain the crazy diversity of all the galaxies we see. The theory needs a way to adapt. And this is where something called a screening mechanism comes into play. The paper calls it the minimal pore sector, or MPS. The idea is pretty intuitive. Wherever you have a ton of normal matter packed together, like the dense center of a galaxy or even our own solar system, it sort of pokes holes in this dimensional field. It suppresses it or screens it.
And that's the key. It's why we don't feel this fifth force here on Earth, but it can still be a huge deal way out in the sparse, empty regions of a galaxy.
So, we have this radical idea, a mechanism, a testable prediction, and a screening model. But none of that matters if it doesn't match reality. The ultimate test is always, how does it hold up against the cold, hard data? So, let's have a look.
Wow, okay, check this out. They tested this new model against 175 real galaxies. What we're looking at here is a win rate. Basically, which model gives the best explanation for the data without being overly complicated. And the results are, well, pretty stunning. This new dimensional theory, labeled MPS, comes out on top almost half the time. It's actually outperforming both its main rival, MOND, and the standard dark matter model.
And for those of you who love digging into the numbers, here's the full breakdown right from the paper. You can pause and look at all the stats, but the main takeaway is that across the board, this new framework is seriously competitive. In many cases, it's providing a superior fit to the real galactic data.
Now here's a peek at why it performs so well. A known issue with MOND is that it sometimes overpredicts the speeds of stars way out at the edge of galaxies. This new theory, though, it doesn't have that problem. That very specific fall-off rate we talked about earlier naturally keeps the model's predictions right on the money, even in the deepest, darkest reaches of a galaxy.
And the paper's author just puts it perfectly right here. The fact that the model fits so well suggests that this thing we've been calling missing mass for decades might not be mass at all. It could be a purely geometric effect, a direct consequence of the way space itself is behaving on these huge scales.
And what makes this so compelling as real science is that it's completely falsifiable. It's not a vague, hand-wavy idea. It makes these incredibly sharp, non-negotiable predictions. First, it says there's this rigid force law that has to weaken exactly proportional to r to the power of -10/9. Second, the underlying field itself has to weaken as r to the -1/9. And finally, that screening effect has to line up perfectly with where all the normal matter is. If our observations get better and we don't find these things, well, the theory's toast. And in science, that's a feature, not a bug.
So where does all this leave us? Well, we have a compelling, mathematically coherent, and data-supported alternative to dark matter. It's a theory that says maybe we don't need missing mass, maybe we just need a dynamic geometry. And it leaves us with this fascinating, kind of unsettling final thought. If the very dimensionality of space isn't fixed, what else have we been taking for granted? What other constants of nature are actually just dynamic parts of the cosmic machine?